All right, everybody, we're going to do Fall 2020 Test 2, Part 4. This is the early version. It's the first one you'll encounter as you open up the document. Question 5 has a big molecule. I will leave it up to you to do the R and S. Maybe at a future date, we can do some more practice on those. But I think we're going to focus on this new material right here that has to do with optical rotation. Now, we have to have our units for concentration match those of what you learned to be the units of density. So concentration has to be grams per milliliter. And we don't have grams, we have milligrams, which is very common in pharmacy and medicine. Drug doses are almost always milligrams. And in the lab, our balances are almost always in grams. So we have to become experts at interconverting from milligrams to grams and grams to milligrams. One mistake is too many when we're talking about drug doses. All right, enough pontificating. Remember, 1,000 milligrams is a gram, and this appears to be 1/2 of that. So we're talking about 1/2 of a gram. Half gram. And there's our milliliters there. So we're just going to put the C over here. Remember, no calculators. And these fractions in these problems are not overwhelming. We can simplify that to 1/20. 1/2 over 10. It's 1/10 of 1/2 is 1/20th. And then the path length is almost always given in centimeters, but it needs to be in decimeters. So just remember, a decimeter, there's actually 10 decimeters in 1 meter. And there's 100 centimeters in 1 decimeter. Sorry, 1 meter. I said that wrong. Apologize. 100 centimeters. These are definitions. This takes 10 decis to make 1. It takes 100 centis, like 100 cents in a dollar. So it looks like a decimeter is twice as big as this. 10 times as big. I'm not talking well today. Twice as big. I said it again. 10 times as big. Whatever you have in centimeters, move the decimal one, and you've got your decimeters. Make sure you move it the right direction. All right, I think we're set. The temperature is irrelevant in these questions, but if you're doing this experiment in the lab, you need to make sure that when you're doing your optical rotation, you match this value because it does vary over temperatures. This is the alpha observed here. Let's go with green. We got green, purple. That is the observed rotation under non-standard conditions. These are not standard because that's not 1 gram, that's not 1 milliliter, and this is not 1 decimeter. So we have to correct our observed rotation and make it standard. That's what the square brackets means. So part B starts this way. To standardize your rotation, you take the observed rotation, which was +5 in this problem, and you divide by C, which we worked out to be 1/20, and multiply it by L down there, which was 5. Keeping in mind the standardizing an alpha equals the observed alpha over C times L is an equation you must know. And we got a lot of good simplifying down there. 5 divides by 5, and you get 1/1. So this is now 1/1/20, which is 20. And that proves to us that we don't have a pure sample. We have a mixture. because that number is less than this number. If it was positive 50, that would mean we had 100% molecule X. If this number here was negative 50, it would mean we have 100% enantiomer of X. And we have less than that, as you will on the test. Your number will never be that number. There's no fun in that. So we have to do part C and do the optical purity, which is defined as the percent enantiomeric excess. Your other equation you need to know, you take your standard alpha observed, which I forgot to write in the previous one. Standard alpha observed is what we calculated in part B, and you divide by the standard reference value, which I must give you, and you multiply by 100 to make it a percent. And we don't like negative percent, so we put an absolute value around the calculation. And this seems like it's going to work out fairly nicely. We have a 20-degree standard observed rotation, and the reference is right up here. It's 50. And absolute value times 100. Well, even without a calculator, this is not too bad. 100 over 50 is 2 times 20 is 40. And this has only one meaning. It means there's 40% more of the major enantiomer than the minor. That's the only way to read that. Okay. And there's something we could have done from the beginning of the question without any math. And I always do it out of order. I look at the sign. I use a highlighter. I look at the sign of the rotation. It's plus 50 there. And it's plus 5 here. Those signs match. So plus matches plus. And put some highlighter action on them. So molecule X is major. If the signs were a mismatch, one of them plus, one of them minus, doesn't matter which, then molecule X's enantiomer would be major. And that's your only two choices. Either it's X or it's enantiomer that are major. So I have 40% more of X than its enantiomer, and the total milligrams was 500. So first, let's figure out what 40% EE means in terms of what percentage of each isomer there is. Here's how I look at it. You could do algebra with two numbers that add up to 100% because there's only two molecules, and they subtract and give 40. That's one way to do it and solve. Or you can say 40% X plus the other 60% of the solution is the part of the solution that's invisible because it's racemic. If you haven't read or watched videos about racemic yet, you should, but that just means a mixture that's equal amounts of either of both enantiomers. So we write the word racemic here. And just keep in mind that part of the solution that's racemic gives you 30% more X. It also gives you 30%, which is half of that, enantiomer. And before I move on, I hope I didn't lose anybody. Where'd the 60 come from? Well, you got to have 100%. The total's 100. We calculated 40% was the excess. The other 60% is the part that doesn't rotate light. It's the racemic part. So we only care about X in this question. In fact, it will be the only way I ever ask this question is about the molecule in the picture. So here we go. I don't care about the 30% enantiomer anymore. We have a total of 70% X. And we have a total of 500 milligrams. I want this to both be in what percentage of the sample is X and how many milligrams is that? Okay, well, we got the percent. How do you get milligrams without a calculator? It's not that bad. We have total of 500 milligrams. 500 milligrams. I love fractions. I learned to love them. They're good for us. I know that 70% can be broken down to 50% plus 10% plus 10%. Those are easy numbers to find from the total. What's 50% of 500? It's 250. That's half of 500. 10% is the easiest one, isn't it? Just slip the decimal one. You got 50. And another 10, 50. So your answer is 350 milligrams. Your other answer was 70%. And that is the end of that portion of the problem. And